All right, Yunzhi, please go ahead to start. Maybe you can introduce yourself.
Sure. Sure. Can you see the slide?
Yes.
Okay. Okay. Thank you for the invitation. Very be glad here to present our SSO events and also analysis. Yeah, I'd like to talk a little bit about myself. So I got my bachelor and master degree in power system from Shanghai Jiaotong University in China, and I worked there 3 years, and then I came to UT Arlington to pursue my PhD degree. After that, I worked for the consulting company, DMV, for 5 years, and I joined ERCOT about 11 years ago. So in ERCOT, I was in planning for 5 years and 6 years in operations. Right now, I'm leading the team of operations stability analysis. Basically, we have two teams in ERCOT that are dedicated to power system stability. One is the planning side, another one is the operation side. So I'm leading the effort in the operation side. We basically study the stability issues in the operational horizon. So in this presentation, I will talk about ERCOT and the ERCOT RBRs related to the sub-synchronous oscillation. And in general, we have two types of SSO events and studies. One is related to the series compensation. Another one is weight grade related or system strength related. And at the end, I will talk about the large load and also the large load SSO events in ERCOT, which is pretty new. So about ERCOT, just quick, ERCOT is nonprofit. We don't own generation or transmission, and system reliability is our top responsibility. As you can see from here, we have no AC connection with other grid. We are kind of pretty much isolated. The total DC connection with other grids is only 1.2 gigawatt. And compared with our peak load, which is 85 gigawatt, it's very kind of negligible. We have a lot of renewables. We have about 40 gigawatt wind and 30 gigawatt solar. And the maximum wind penetration is close to 70%. Maximum solar penetration is over 50%. And the combined wind and solar penetration record is about 76%. So it's pretty challenging for a grid, isolated grid. And we also have a lot of batteries. We have 10 gigawatt of batteries now. Some forecast for the future RBRs. So wind is kind of slowed down. So even after 2-3 years, it still be like 40 or 40 something gigawatt. And solar is booming. We have 30 gigawatt, but it could be doubled in the next 2-3 years. Similar for the batteries, we have 10 gigawatt batteries. It could be tripled in the next 2-3 years. So imagine, right, for ERCOT system, we are pretty much isolated and peak load 85 gigawatt, but our wind, solar, and battery, the RBR together, we could have like 40 gigawatt wind, 60 gigawatt solar, and 30 gigawatt battery. So together, the total capacity of RBR will be 130 gigawatt in the next 2-3 years. It's pretty challenging for us to integrate such big amount of RBRs. Before talk about ERCOT event, I'd like to talk about a little bit about our RBR SSO task force. Dr. Ling Fan and me create this kind of task force 2018, and we have many panel sessions, and also we published a task report for wind SSO in 2020. We also published 2 transaction papers, and one important one is real-world SSO events with high penetration of RBRs. In this paper, we basically try to review all the historic RBR SSO events, kind of create categories of 2 categories. One is related to the series compensation. Another one is really related to the system strength or weight grade. A typical example in 2009, we have South Texas SSO event related to a Type 3 wind farm and series compensation. And then in 2015, there's Northwest China SSO event related to the high penetration of RBR in weak grid. And this table shows some reported RBR SSO events. As you can see, most of them are related to either Type 3 wind farms with series compensation or high penetration of RBR and weak grid condition. And as you can see, we have both such kind of oscillation. We have series compensation oscillation, and also we have weak grid oscillation. About the weak grid oscillation, we call sub-synchronous, series compensation related to the oscillation. We call sub-synchronous control interaction. It's an interaction between series compensation and control system of generation resources. It's a purely electrical phenomena, pretty fast, and typically the Type 3 or defect wind machines is more vulnerable to the SSCI. It is really because induction generator effect. So this is the equivalent circuit of defect machines for SSR studies by Professor Xie from Tsinghua University. I think this one kind of explained the SSCI pretty well. Basically, you have the rotor resistor, which is positive, but the slip is negative for induction generator. So that's why it's called induction generation effect. And then you have the converter, which add another K here. So basically make the induction generation effect more severe. So that's what we try to say. The RGE effect could be exacerbated by the converter control. So that's kind of the reason of this SSCI. We have many series compensation in our system. That's why we have SSCI events. We have 4 series compensation in South and 14 in West Texas. And this is our first event, South Texas 2009 SSCI event. It's probably the first event in the world that really triggered a lot of studies for SSCI. I think before this event, we really don't know that the wind farm could be oscillated against series compensation. So the event pretty simple. Basically, there's series compensation between real Hondo to long hair line, and Aho is a cutting station with a lot of wind farm connected. I believe they are all defect machines. And then we have a fault along the line of Aho to long hair. So this line tripped. So all the wind farm became radially connected to series compensation, and then the SSCI happened and caused high current and damaged both series compensation and the wind turbine generation. So this is the first event. As I said, this event really triggered not only the industry, but also the research committee to really try to understand what is the phenomenon, like why we have these issues. So then in ERCOT, since we have a lot of series compensation, so we try to propose our study framework, which is a 3-step study framework. We first try to run topological screening to identify the contingency we call M-X that could lead the radio connection. Because based on our experiences, the radio connection is the most challenging or conservative condition for the SSCI. So we first try to find out how many outage or contingencies that cause the radio connection. And if that number X is very big, then we will conclude no SSR risk. Otherwise, we will go to the second step, which is frequency scan. We run the frequency scan and then compare with the frequency scan criteria. If the meet the frequency scan criteria, then we conclude there's no SSR issues, and that's it. Otherwise, we will go to the third step, which is the detailed PSCAT simulation to identify the real SSR risk or SSCR risk. So I'll talk about a little bit step by step. The topological scan is pretty straightforward. we basically count outage for the radio connection. But in this one, it's very simple. If you trip line A and line B, right? So then the generation Y will become radially connected to the series compensation. In actually, most of the time, we can use our eyeball to count the contingency or outage for the radio connection, but sometimes the network is complicated. So we propose an algorithm based on classic for the focus on maximum flow minimum current series to find out the minimum X that lead to radio connection. Like in this example, if we trip double circuit between bus 3 to bus 5 and single circuit between bus 4 to 7. So under M-3 condition, this generation will be radially connected to the series compensation. And then about the frequency scan, right? So if the M-X number, that X number is small, then we run the frequency scan. And usually we run the frequency scan at the point in the connection of the generation. And then we run the generation side frequency scan in PSCAD. And then we run system side frequency scan, either in PSCAD or in PSE. We prefer PSE, or talk about like why. And also for system side or grid side, we need to study the contingencies. And once we have impedance from the system side, and then we add to the generation side, and so we have total impedance. And after we have total impedance, then we look at R and X. Basically, we look at the reactance X crossover from negative to positive. In this example, right, the X cross 0 at 30 Hertz. And then we look at the resistance at crossover frequency at 30 Hertz in this example. And if the R is positive, that means no SSCR issues. If it's negative, then there's SCR issues. How to run the frequency scan? So for the grid side, since it's RBR, so we have to use a perturbation analysis to do the frequency scan. The idea is to reject a wide noise signal voltage current at sub-synchronous frequency spectrum, then run FFT analysis to calculate the impedance at a sub-synchronous spectrum. So this is an example of the typical defect machine R and X across the sub-synchronous frequency spectrum. You may want to focus on this blue curve, which is the resistance. As you can see, the defect machine at the sub-synchronous frequency spectrum, they are most negative. So that's kind of the reason of the SSCI relate to the defect machines. And the system side, as I said, you can use PSCAD or PSE. The reason we use PSE because we can apply different contingencies. Sometimes we could run 1,000 or 10,000 contingencies. It's very hard doing the PSCAD. Doing PSE is pretty straightforward. You can use Python script. And the main idea is to scale the impedance of the transmission line, transformer, and series capacitor and shunt capacitor. And this is the formula we use to scale the impedance of the lines, transformers, and capacitors. And after that, we can run the short circuit analysis to obtain the system impedance. It's very straightforward, but you need the Python script to do it. And this is our example, or we have a tool to run the frequency scan, and we have used this one for hundreds of SSR studies. So example here is, you have waveform 1, and then if we trip double circuit between bus 5 to bus 6, and then double circuit from bus 1 to bus 7, and then this waveform will be really connected to the series compensation. And then we run a frequency scan and under this condition. So this waveform impedance, and then this is the other side is the system side impedance under the M-4 contingency. And then, as I said, we add them together. What we found is, so the reactance will cross from negative to positive at 8 to 9 Hertz. And at crossover frequency, the resistance, the blue one, is negative, which indicate risk of SSCI. And then we perform a PSCAD study for the same contingencies, and then we do observe the SSO phenomena, and we also run FFT studies using the current, and the FFT indicate the oscillation is 9 Hz, which kind of matching with frequency scan. So basically for SSCI, look like frequency scan is pretty good screening tool. Well, so far, everything is good. However, after that, so after we do this kind of studies, also we require the new RBRs to go through the SSR studies. We still have a few SCCI events. So these are the events in South Texas in 2017. And they are all related to the radio connection condition. So you either trip this line between station 4 to station 5, then these two power plant radio to the service compensation, or you trip the line between station 2 to station 3, then these two wind farm became radio connect to the service compensation. And we have 3 events, and we have either undamped oscillation or damped oscillation. Basically, SCCI events happen, and all the wind turbine here, they tripped because they have SCCI protection. So they tripped, but this is kind of not good for us because, as I said, all the wind farm here, they have simulate the SSR, and the simulation in PSCAD show no issue, but in reality, we have issues. I think later we coordinate with the plant owner. I think they try to attune the controller. Basically, all this wind farm, they have a SSR mitigation controller. I think they try to tune the controller, and after that, it was okay until 2023. Same location. There's another oscillation in 2023. And now it's a little bit more complicated because, as I show, right, in ERCOT, we keep add more RBRs. So they're in the same location, but we have more RBRs, and not only defect machine, but also we have type 4 or full converter machines. And then same thing, we have radio connection because of some outage. And then SSO happen again at, and the frequency is about 30 Hertz. So all series compensation here, they have SSR protection. So the protection kind of automatically bypass the series compensation. So again, no damage, but still, it is kind of unexpected. As I said, all the wind farm here, they have gone through the SSR studies, and the simulation show no issues. So that's why I put some kind of slides to show the challenge. It looks like it's very hard to replicate SSCI event in PSCAD simulation. And I think the reason we have the events is really because the tuning SSO damping control with change system condition is very challenging. I'm not saying it doesn't work, because we still have one private owned series compensation, and they have defect machine connect to them, and they have been operating for more than, I don't know, maybe 10 or 15 years, and it works fine. But here, I think this is just my own opinion. I think because we keep at new RBRs with different OEMs and facility owners, it's very hard to make sure the existing SSO damping control works with different operational conditions. So this is, again, this is my personal opinion. But anyway, since we have seen this kind of SSR issues or SSCI issues in real time, so we bypass that series compensation in South Texas. And also recently we try to propose some market rule change to prevent the future generation from interconnection if the generation become radially connected to the series compensation under M-1 condition. However, this change, the PGR is still under discussion. Not sure if this one will be passed or not. So this is a series compensation related SSO. And then second one, I will talk about the weak rate or system strength related SSO. It is also not new. It happened to ERCOT a long time ago. But this event's more a local event. It's a type 4 wind farm connect to a 69 kV. We find out because there's transmission outage, the short circuit ratio dropped from 4 to 2, and then we observed the oscillation. I think the oscillation frequency is about 4 Hertz. It's a type 4 wind farm, and we were able to replicate that in the PSC studies, and we also try in a simulation to tune the wind controllers to damp out the oscillation. As I said, this event is local, but the problem is we have more and more RBRs, right? As I mentioned before, right now we have about 80 gigawatt RBRs, wind, solar, and batteries, and in the future will be more and more. So there's concern that this local weak rate issue probably become system-wide or at least a regional-wide. For example, we have 2 areas. One is West Texas, another one is South Texas. They are both kind of far away from load center, which is in the middle. We have DFW, Austin, San Antonio, and Houston. So there's long distance transfer, and also in West Texas or South Texas, we have limited synchronous machines. And also usually when the wind and solar dispatch is very high, it's very hard for synchronous machine to compete with them, so they may choose turn off. And we have in operation and planning, we have seen increasing stability concerns in both West Texas and South Texas. We try something like the system strength studies and even in real time. So this is an area called Panhandle, which is far away from the load center, kind of at edge of the system. There's no synchronous machines, there's no load, and all resource there are RBRs. It was 4 gigawatt at the time, now actually more. We know there's system strain issue, so we add 2 synchronous condensers, each one 175 MVA, but still, we still find out the system is still weak. So then we propose the idea to calculate WCR, weighted short circuit ratio, in real time based on the Panhandle RBR actual output. And then we set up 1.5 as the limit. Basically, if WCR is dropping to 1.5, then we will curtail the Panhandle RBRs to make sure the WCR is always about 1.5. We keep this one in operation for a few years, but we retired this one in 2021 with the transmission system upgrade in Panhandle. But it's not say that Panhandle grid is not weak. I think it's still weak because even we add transmission upgrade, we have more and more RBRs adding to the Panhandle. But the problem is we really cannot find a good index like WCR that can work. So we try WCR up this transmission line. We find out that we basically cannot identify a good limit that we can use in real time to make the minimum system strength for this area. So that's why we retired this WCR. Last year, we proposed 6 additional syncons, each one 350 MVA to West Texas to increase system strength in West Texas. We also try to run PSCAT, like parallel simulation, to identify any potential control stability risk, basically some kind of a oscillation at sub-synchronous frequency range, which may not be able to be captured in the IMAX domain or PSC simulation. And this is the interesting study that we recently did. It's a very great issues. So we have 6 RBRs, total capacity 2,000 megawatt, under a P7 plus P7 events, which means we trip double circuit here, and then trip double circuit in the south. So all 6 RBRs will connect to bus 4 through very long lines with series compensation. But in this one, it's not really SSI issues. The series compensation here actually helps the stability performance. So if we bypass the series compensation, the performance actually worse. So which indicate the issue here is really system strength. And we calculate WCR, the value is only 0.85, 0.85. And we run both PSC and PSCAT studies. We find out that PSC limit is actually low. The PSCAT, I'm sorry, PSC limit is very high. The PSCAT limit are significantly lower than PSC. And even also we try if we can add more machines or RBRs into this area, we actually find out if we add another RBRs, it will not work. Even we curtail all the RBR in the local area to very low, like 10% or 5%. We still have unstable oscillation with the new addition of RBRs. It's because your WCR will be very, very low after a new RBRs. This is the SO event. We have, I believe, probably 20 to 30 hertz oscillation. And again, as I said, it's not really related to series compensation. So to kind of overcome this kind of weak grid issues, we try to propose grid forming batteries. I think there are already a lot of discussion about grid forming, so I will just quickly go through this. In theory, grid forming basically try to maintain internal voltage phasor in magnitude and also angle that is constant or nearly constant in sub-transient to transient time frame. We evaluate the potential application of grid forming batteries in ERCOT, and we use multiple cases, and we find out the stability performance can be significantly improved with the grid following battery replaced by grid forming batteries. We published 2 IEEE PS general meeting papers and 1 secret paper. We also try to develop a weak grid test case, and then we share as a Google Drive for others if they are interested to test weak grid test case. We contract electronics to help us develop the function specification and test framework for grid forming. So here called advanced grid support, which is basically grid forming. And we also propose a NERGA 272 to require the grid forming capability for future batteries. However, this NERGA is still under discussion. Okay, so that basically I covered the RBR SSO. One is related to the series compensation, another one is related to the weak grid or system strength. The last one I talked about our large load. In ERCOT, large load is defined as a load more than 75 megawatt. They are mostly crypto mining center, data center, and hydrogen productions. Right now, most of our existing large load are crypto mining centers. We probably have a few data center. Hydrogen, I don't think so. We already have a lot of large load. Right now, the total operational capacity is about 5 gigawatt large load. And in the future, look at the forecast, it's huge. It could be 99 gigawatt. Again, this is based on the forecast. And imagine, right? Our peak load right now is only 85 gigawatt. So it's kind of double the load. Anyway, So that's the large load, but I like to talk about some large load events. So since July 2024, for one large load, we observe their oscillation all the time, especially when the dispatch or consumption is very high. Initially, we identified this one in the EMS. So the frequency, I think, look like it's like 8 hertz or something. But later we request the DFR data, and it shows oscillation frequency is about 23 hertz. And both ERCOT and also the TOs, transmission company, confirm the load is the source. And what we find out, if we limit the load below 300 megawatt, then the oscillation will go away. So you can see from here, right? So we have oscillation 25 peak to peak when the consumption is between 300 to 350. And if we reduce the consumption of the load, that oscillation kind of goes away. So we kind of engage with the load owner and operator, and they did an operational test. And they determined that it's a firmware issues. They said some older firmware version on certain equipment is the root cause of the oscillation. And then they updated the older firmware. After that, even the consumption is about 300 megawatt, we have not observed any oscillation. But for this one, we at this time we are not very clear about this. We are still kind of try to talk to them to understand more about this. But what we can see is really based on what they say is a firmware issue. I think that's all from my side. I'll be happy to answer if there are any questions.